Hey everyone, today we'll look at overview of disjoint and let's try to see what we can understand why we are using this disjoint set. I have read in the past, but I'm just going through it and revising it one more time so that so I can don't forget it quite often. So let's start. Given the vertices and edges between them, how could we quickly check whether two vertices are connected? For example, figure 5 shows the edges between vertices. So how can we efficiently check if 0 is connected to 3, 1, 0 is connected to 3, 1, 3 and 1 is connected to 5, or 7 is connected to 8? We can do so by using disjoint set. The structure also known as union find data structure.
Hey mate.
Upar. We can do so by using the disjoint set data structure, also known as union find. So how can we efficiently check if 0 is connected to 3, 1 is connected to 5 and 7 is connected to 8? Okay, we can do so by using disjoint set, also known as union find data structure. Note that other might refer to it as an algorithm. In this explode card, disjoint set refers to a data structure. The primary use of disjoint set is to address the connectivity between the components of network. So the primary use of disjoint set. Okay, the network here can be computer network or a social network. For instance, we can use a disjoint set to determine if two people share a common ancestor. Got it. Okay, so terminology: parent node, the direct parent node of a vertex. For example, in figure 5, the parent node of vertex 3 is 1, and the parent node of vertex 2 is 0, and the parent node of vertex 9 is 9. Okay, here. Root node, root node, root node, a node without a parent node. It can be viewed as parent node of itself. For example, in the figure 5, the root node of vertex 3 and 2 is 0. As for 0, it is its own root node and the parent node. Likewise, the root node and parent node of 9 is itself. Sometimes the root node is referred to as a head node. Okay. Summary of video: how do disjoint works, solving the connectivity question in figure 5. Okay, let's see this video. Okay, I can't see my headphones. Where is it? Connected, right? So why is it not available here? Hello.
How do we check whether two vertices are connected? For example, let's say that you want to check if node 3 and node 0 are connected. Even though they're indirectly connected, they're still connected. By connection, it can be a direct one or an indirect one. How about nodes 2 and 8? Are they connected? The answer is no. However, for node 5 and 7, they must be connected, right? These facts are not hard to tell by just looking at the graph, but when there's thousands of vertices, you won't be able to tell by simply looking at the graph. In that scenario, we'll need help from the computers. So how can we solve this? I gave the answer at the beginning, which is using disjoint sets. Now let's look at how it works. Initially, we have 10 vertices labeled from 0 to 9. We want them to be independent and isolated. The first thing we need to do is connect the vertices. Let's connect 0 and 1, or make them a union, and save them into a set. We have to do something here, which is to choose a vertex as the head of the set. We can either choose 0 or 1, it doesn't matter. Let's say we choose 0, meaning the head of this set is 0. Then we will connect nodes 0 and 2. 0 is already in the set on the left, but 2 is independent by itself. We're going to connect 0 and 2, so we're going to add node 2 to this set, and this is what happens. Now, if we check the heads of nodes, we will find the head of node 1 is 0, and the head of node 2 is also 0. Because they're both in this set, both their heads are node 0. Now let's connect 1 and 3. Since node 1 is in the set on the left side, all we have to do is add node 3 to this set, which increases the size of this set. Now, when we try to find the head of 3, it will again be node 0. And then we're going to connect 4 and 8. Node 4 is isolated, and 8's also isolated, so we can simply merge them into the same set. Since we just created a new set, we need to find another head for this set. Let's choose 4 as the head. Next, we're going to connect 5 and 6. Since 5 and 6 have not previously been connected, we will have to create a new set. Between 5 and 6, we have to choose a new head for this set, so let's choose 6. Next, we'll connect 5 and 7. 5 is in a set with 6, so if we want to connect 7 and 5, we want to put 7 into that set that contains 6. At this time, if we're going to find the head of 5, we'll get 6, and if we want to find the head of 7, it's also 6. For 8, its head is 4. If we want to find the head of 9, since it's an isolated node, the head of it is simply itself. In a way, we can say 9 is in a set by itself, so therefore the head of 9 is 9 itself. After the union operations, we have connected all the vertices. Now we are ready to check whether the given two vertices are connected or not. In other words, we are checking if two vertices are in the same set. For the first example, we have nodes 0 and 3. For 0, the head of the set is 0. 3 is also in this set, so its head is 0 too. We realize that since they have the same head, they must be in the same set. And then let's look at 1 and 5. For 1, it's in this set and the head is 0. But which node is the head of the set that node 5 is in? It's 6, and we see that 0 is not equal to 6. That means they're not connected, which we can see that they're not in the same set. Next, let's take a look at 7 and 8. For 7, its head is 6, and for 8, its head is 4. We see that 6 is not equal to 4, which means they're not in the same set. At this point, if we were to connect 0 and 5, 0 is in this set, and 5 is in this set, making a union of nodes 0 and 5, which means that we're connecting the two sets together. Now we just have to merge the sets together to form a bigger set, like this. We will also have to choose a head among all the numbers in the set. For example, if we choose 0 as the new head, 6 will no longer be the head here. Let's look at 1 and 5 again. For 1, the head of the set is 0, and for 5, the head of it is also node 0, so they're now connected. So as you can see, this is the basic idea of a disjoint set. Thanks for watching.
In this video, we'll talk about quick find implementation of disjoint sets and cover its two basic operations along with their complexity, find and union. Okay, so let's see what this guy has to say.
Hello, and welcome to this Leetcode video tutorial. In the previous video, we discussed that to implement disjoint sets, we will use the root array to store the parent node or vertex. For the find function, Every time we try to find the root node of a vertex, it needs to find the parent node and the parents of its parent node until we find the root node. For example, given this array, how would we find the root node of 4? We have to find the vertex 4 and check whether it's equal to its parent. When they're not equal, this means that 4 is not the root of itself, so we have to search along its parent nodes. Here we find 1. Its parent node is 0, which does not equal 1. When they are not equal, we have to look at the parent of 1, so we find its next parent and check if its parent node is equal to the node itself. When we find that they are equal, we can finally say that node 0 is the root of 4, and it's also the root node of 1. Visually, we will find 4 on the graph and find its parent node, then go to the parent of its parent node until we find the root node. So the root node of 4 is 0. For 1, its root is also 0. So these are the operations we perform in the find function. But doesn't this seem tedious? For 4, we have to find 1, then 0. Then if there's another node 7 under 4, to find the root of 7, we have to check 7, then 4, then 1, and then finally the root node 0. We have to search step by step for the parents. What if we store the root node itself instead of storing the parent node as an element in the array? This means for our find function, we can directly get its root node. Wouldn't this save us a lot of work? To elaborate, let's say we already know that the root of 0 is 0, the root of 1 is 0, and the root of 2 is also 0. For 3, its parent node on this graph is 1, but its root node is 0, so we will change what we store at index 3 from the parent node to the actual root node. Similarly for 4, its parent node is 1, but we don't store the parent node, we'll store its root node. And for 5 and 6, we'll do the same thing and directly store their root nodes. Now, if we want to call find on 6, or find the root of 6, we can just go to index 6 and look at this value. Now we can instantly get the root node, which obviously makes our find function much more efficient. But the trade-off to storing all the root nodes in the array is that every time we do the union operation, we have to perform an extra step. Let's say if 0 and 2 are not connected, now for 5 and 6, their root nodes are 2, and for 2, its root node is itself. This is the case if node 0 and node 2 are not connected. Now if we try to connect 0 and 2, the first thing we need to do is find the root node of 2. Of course, it is 2 itself. After finding the root node of 2, let's choose 0 as our parent node. We'll change the root of node 2 to 0, and now the root nodes of 5 and 6 have changed. It used to be 2, but since the root of 2 has been changed to 0, the root node of 5 and 6 is also 0, so we need an additional step in the union function. That is, when nodes 0 and 2 are connected, and the root node of node 2 is set to 0, we will have to go through all the elements here to find the nodes with 2 as the root, and change the root nodes to the new root node 0. So it's an extra step here in the union function. We have to traverse the entire array, then find the element that corresponds to the root node we're merging with, and finally change the root node to our new root node. This is the extra step. After looking at this idea, let's take a look at the code for quick find. We are using a pseudocode here and not any specific programming language. It's human readable, but it will not compile. You can take this pseudocode and rewrite it in any language. The reason we are doing this is that we want to help people using different languages. So here we will have the union find class, which is the same thing as a disjoint set. Of course, because it's a data structure, we will define it as a class. Initially, we need a root array, which is what we have here. Then we're going to have a constructor, so we're going to have a size parameter in this constructor. Size represents the number of elements in the array, that is, the number of vertices. We'll initialize root to have the size of the number of vertices, so root will initially be filled with zeros. Then we will initialize it. Since we have each vertex isolated by itself in the root array, initially the root of each vertex will be itself. Thus, here we initialize the root array by setting all the elements to their indices. Again, the root node of each vertex is itself. Then we're going to have a find function, which basically takes in x and returns the corresponding value at index x in the root array. Since every element will be pointing to its own root node, we just return this value and then move on to our union function. First, we need to find the root nodes for x and y. When their roots are equal, we know they're already connected, so we don't have to perform the union operation. But if the root nodes are not equal, we now have to go through the entire root array once we see a value equal to the root of y. In other words, when the corresponding root node is equal to the node we are merging, in this case root y, then we have to change this root node to our new root, which is root x. This way we can make sure that each element in the root array will be the root node of that index. Finally, here is a function that determines whether x and y are connected. Of course, this is also very simple. All you have to do is check whether the roots of x and y are equal. If they are the same, they're connected. If the root nodes are not the same, then they're not connected. For find x, its time complexity is O of 1, because we look up the array directly and then find the value through the index, which is O of 1. For the union function, since it has a for loop here, to go through the whole array, its time complexity is O of n, and will be O of n every time because you're going through this array every time. For the function to check for connectivity, its time complexity is also O of 1 because it relies on the find function, and the find function is O of 1, so the time complexity is O of 1. Now we have explained the fundamentals of quick find-based disjoint sets. Thanks for watching.
Okay, so quick union by rank, path compression, then the number of provinces. Got it. Java. What's Leetcode playground? Okay. Okay, let's try implementing our own, but wait a minute, like how will we connect everything? So basically union find will implement that, and let's see if so constructor, we have to pass the size, and this dot array, we are going to store everything in array, right? New array size dot fill 0, and for let I equals to 0, I is less than this dot array dot length, then I plus plus, oops, sorry, and then what we can do is this dot array will match it of I, will match it to I. Okay, so here we have defined everything, and then the find function will be passing x and y, then sorry, just the x, we are going to pass just one node, or let's call it node. So return this dot array of node. Okay, and then union, in union we are matching x and y, then let x is equal to no, node x is equal to this dot ar of, sorry, find of x, and let node y is equal to this dot find y, and for and if node x is not equal to node y, if they are equal then we don't have to do anything, we have to um, do this for let node of this dot add. What we need to do is this dot if this dot add of that node equals to node y, then we need to set this dot add node value equal to node x, and then they'll be equal, and if they are equal, so for like what is the operation for checking connected? Yeah, if they are connected x and y, if return this dot find x equals to this dot find y. So yeah, this is the algorithm for find. Add snippet, no snippet found. Close. What is fork? Saved where? Where did it see? But I don't know. Okay, let's see. So let's go and let's do quick union. In the following video, we'll take a look at quick union implementation of disjoint set and show the difference between quick union implementation and quick find implementation we talked about earlier. As previously done for the quick find implementation, will also derive time complexity of
Hello, and welcome to this Leetcode video tutorial. In the previous video, we introduced quick find based disjoint sets. Overall, in such a disjoint set, the find operation is very fast, but it leaves more work to the union operation, causing the union operation to be quite slow. In this section, I'm going to talk about quick union based disjoint sets, which means that the union operation will be faster, but the find operation will take more work. Let's see how we can make the union operation faster. Given these vertices, we want to perform these connect operations. Let's see how we can achieve that using quick union. First, we need a root array. In this array, the indices represent the vertices, while each element will be the parent node of the vertex. In quick find, it will be the root node. However, in quick union, the element of array will be the parent node. Let's see how we can connect 0 and 1. To connect 0 with 1, the first thing we do is define the root node of 0 and the root node of 1. In the picture, we can see that the root node of 0 is 0, and the root node of 1 is 1. So we know that the root node of vertex 0 is 0, and the root node of vertex 1 is 1. We will choose one of them as the parent node. Let's choose 0. Then we connect 1 to the root node of 0. Here, of course, the root node of 0 is 0 itself, so we will connect 0 and 1 and assign 0 as the parent node of 1. Now let's see how to connect 1 and 2. An intuitive method is to connect 1 and 2 like this, and then assign 1 as the parent node of 2. This is the method we introduced earlier. Now I'm going to introduce a faster method, which involves finding the root node of 1. In this case, it's 0. Then we will directly connect 2 to the root node, which means the root node of 2 is neither 2 nor 1. Rather, it should be 0 because we directly connected 2 to the root node of 1. To connect nodes 1 and 3, we will perform the same operation. The parent node of 3 will be assigned as 0. Now we need to connect 4 and 5. To connect 4 and 5, the root node of 4 is 4, and the root node of 5 is 5. So we need to choose a parent node from them. Let's choose 4, and update the parent node of 5 to 4. Next, let's connect 4 and 6. We will again choose 4 as the root node for 6. At this point, it seems like the elements in the root array are all the root nodes, right? So how is it different from QuickFind? I'll give an example here to show the difference. Let's say I want to connect 1 and 5. To do this, I have to find the root node of 1 and 5. Then I will choose node 0 as the parent node. In other words, the root node of node 1 is 0. Now we have to change the parent node of 4 to 0, which is the root of 1. To do this, we will change the 4 in the root array to 0. The new structure will be like this. Now, for elements 5 and 6 in the array, their parents are both 4. But 4 is not the final root. This is different compared to QuickFind. With QuickFind, the root node is stored directly in the array. However, for Quick Union, we must traverse the parent nodes until we find a node such that its parent node equals itself. Then, we have truly found the root. After talking about the idea behind Quick Union, let's look at the code for it. Here, the root array, as well as the initialization, is the same as QuickFind, so I will skip it. I will focus on the differences in the find and union methods, as they are the major differences between Quick Union and QuickFind implementation. For the find method, we first have this while loop. What is it doing? It's checking if the root vertex is equal to the current element. If they are not equal, we will continue searching through its parents until we find the current index, or when the vertex is equal to its parent. This means we have found the root node, so we can return it. This allows us to use the find method to get the root node of x and move on to the union method. When I go to union x and y, I have to find the root nodes for x and y and check whether they are equal, because if they are, they're already connected. If they are not equal, we want to set the root of y, which is the parent node of the root of y, to the root of x, so that when you try to find the root of x and y next time, their roots will be equal. This means we have connected them together. Here, our find method can have a worst case complexity of O of n. In our union method, it doesn't have the for loop like our QuickFind method. This means that it will not be O of n every time, but it will still be O of n in the worst case. Why? Because we are using our find method here, which has the worst case time complexity of O of n. So for the union method, its worst case time complexity is also O of n. So here, for union operation, its time complexity is actually less than or equal to O of n. The operation to check whether to connect the two nodes will be O of n worst case as well, because it calls the find method. And that's all for the implementation of quick union based disjoint sets. Thanks for watching.
Okay. So yeah, the only difference between quick find is like we are just returning this, and in quick union we are doing the heavy computation here instead of here. Okay, let's see what they have to say next. Why quick union is more efficient than quick find.
Hello and welcome to another Leetcode video tutorial. In this video, I'll explain why quick union is more efficient than quick find. Here, the code on the left is quick find, and the code on the right is quick union. There are two major differences between the code snippets. One is the find function, and the other is the union function. This is the find function, and this is the union function. The rest of it is the same. For quick find, the find function on the left has a time complexity of O of 1 because it stores the root nodes for each corresponding vertex in the root array. So for the find function, its time complexity is O of 1. For the union function, its time complexity is O of n because each time we find the root nodes of x and y. Here we have a for loop. We have to iterate the root array from left to right, so we get a time complexity of O of n. So for the union function, it has a time complexity of O of n because it has to go through the entire root array. Now let's look at quick union. For quick union, we observe that the worst case for the find method is O of n. So what is the worst case? The worst case scenario is when the tree is constructed like this, in a line. So to find the root of 4, we have to search node 3, then 2, and finally 1. So in this case, it's O of n. So this will be our worst case scenario. The union function's runtime will depend on the find function. Because the time complexity of this step is not significant, we already know that the find function has the worst case O of n, but this is based on the worst case scenario. So the overall complexity is less than or equal to O of n. For the quick find function, if we want to connect n elements, what will be the complexity? Since each union operation calls the find method, each union will take O of n time, so its overall time complexity must be O of n squared. But for quick union, to connect n elements, the worst case runtime for each union is O of n. So overall, the time complexity is less than O of n squared. So this is why quick union is more efficient than quick find, because only in the worst case is it O of n. This is why quick union is more. So overall, but for quick union, to connect n elements, the worst case runtime, each union operation calls the find method. Each union will take O of n time, so its overall time complexity must. For the quick find function, if we want to connect n elements, what will be the complexity? Since each union
So we have to connect n elements.
Operation calls the find method, each union will take O of n time, so its overall time complexity must be O of n squared.
Okay, got it. O of n squared, yep.
But for quick union, to connect n elements, the worst case runtime for each union is O of n. So overall, the time complexity is less than O of n squared.
Yeah.
So this is why quick union is more efficient than quick find, because only in the worst case is it O of n squared in time complexity. Of course, between quick union and quick find, we're just choosing the lesser of two evils. Neither are very efficient. We'll follow up on this later and optimize our union find even more. Thanks for watching.
Okay. Union by rank. We have implemented two kind of disjoint sets so far. They both have concerning efficiencies. Especially the quick find implementation will always spend O of n time on the union operation, and in the quick union implementation as shown in figure 6. It is possible for all the vertices to form a line after connecting them using union, which results in the worst case scenario for the find function. Is there a way to optimize these implementation? Of course there is. It is the union by rank. The word rank means ordering by specific criteria. Previously for the union function, we always chose the root node of x and set it as a new root node for the other vertex. However, by choosing the parent node on certain criteria by rank, we can limit the maximum length height of each vertex. To be specific, the rank refers to the height of each vertex. Okay. Let's read this. However, by choosing the parent node on certain criteria by rank, we can limit the maximum height of each vertex. To be specific, the rank refers to the height of each vertex. When we union two vertices, instead of always picking the root of x or y, it doesn't matter as long as we are consistent. As the new root node, we choose the when we union two vertices, instead of always picking the root of x or y as the root node, we choose the root node of the vertex with a larger rank. We will merge the shorter tree under the taller tree and assign the root node of the taller tree as the root node for both vertices. In this way, we efficiently avoid the possibility of connecting all vertices in a straight line. This optimization is called disjoint sets with union by rank. Okay. 0, 1, 2, 3, 4 5 line graph.
Hello, and welcome to another Leetcode video tutorial. In this video, we will talk about union by rank. First, let's look at this problem. If we were to connect these vertices using quick union, the previously mentioned method, what would happen? First, we connect 0 and 1. I'll choose node 1 as the root node, or the parent node, so I will put 1 on top. And then 0 goes here, so that 1 is the root node, which is the parent of node 0. And then we're going to connect 0 and 2. The first thing we have to do is look at the root node of node 0, which is 1, so we're going to merge 1 and 2. At this point, we choose 2 as our parent node, so we will put 2 above and do the same thing for 3 and 0. We'll put 3 on top, and for 0 and 4, we do the same thing and write 4 on top. Again, for 0 and 5, we'll choose 5 as our parent node and put 5 on top. Now you can see that this tree is just a line. Each node has only one child. We know for the find function that its time complexity is O of h, where h is the height of the tree. You can see that this tree will lead to the worst runtime scenario for the find function because the height of the tree is equal to the number of all vertices, so it becomes O of n. If we can make this tree more balanced, like this, then the time complexity decreases because h is smaller. This is due to the tree on the left, which has a height of 1, 2, 3, 4, 5, 6. But for this tree on the right, the height is 1, 2, 3. It's clear that the find function on this tree will have a lower or better time complexity. If we can try to balance the tree during union operation, without a doubt, it will help speed up the find function a lot. It will also improve the overall efficiency of the disjoint sets. So is there another way to balance the tree? Of course. Let's say that we have two trees here, and I want to connect nodes 1 and 6. The first thing I'm going to do is define the root node of 1, which is 0, and then we're going to find the root of 6, which is 5, and then we'll choose either node 0 or node 5 as our root node. I drew out the two scenarios. This tree is when 5 is chosen as the root node. What is the height of this tree? 1, 2, 3, 4, 5. So this tree has a height of 5. For this tree, I chose 0 as the root node, and its maximum height is 1, 2, 3, 4. So 4. The tree on the right side is shorter and thus more efficient. So how do we decide that 0 will be our root node? Now you see, for these two trees, the tree on the left has height 1, 2, 3, 4, so 4. And for the tree on the right, it's 2. If we choose 0 at this point as our root node, we can just connect 5 like this. So for this tree, its height doesn't change because we're just connecting a tree with a height of 2 to it. For this path, it's 3, but it has a longer path of 4, so its height didn't change. However, if we connect 0 to 5 and choose 5 as the root node, at this point the height of the tree is already 4 because of node 0. By making node 5 as the root node, the height of the tree now becomes 5. Thus, it made the tree taller. So what is our criteria to choose the parent node? It turns out we just have to look at the corresponding trees. We will choose the root node of the taller tree as the new root node. In this case, the tree that 0 belongs to is taller, so we will add the shorter tree, where node 5 is at, to a subtree of the node 0 and choose 0 as the root node. This way, we can try to make the tree as balanced as possible instead of creating a tree like this. This is the concept of union of rank. We will make our decision based on the height of the tree. Whichever is the tallest will dominate the rest and become the root node. Of course, the find function still has a worst case runtime of O of h. Note that union by rank is a technique that only applies to quick union based disjoint sets, because for quick find based disjoint sets, the find method will always have a runtime of O of 1. Even if the tree is like this, the find function will still be O of 1 constant time. Therefore, union by rank is an optimization for quick union based disjoint sets. We mentioned earlier that union by rank is created for disjoint sets, and more specifically, it is designed for the union function because here in the process of merging, we are trying to balance the tree, which is also an optimization for the union function. Now, let's take a look at the code for it. It's basically the same code we used before for quick union. We only made a few minor changes. First, we have a root array, which appears in all different implementations. Now we are adding a rank variable. We use the rank array here to record the height of each vertex, which is where they are in the tree, and then we have a union find constructor. This was also there previously. The root array will still store the parent node for each vertex, and the rank array is initialized to 0 since each node is isolated at the start. Thus, each of them has a height of 1. So in the beginning, we set the rank for each vertex to be 1, and then we'll look at our find function. This is the same as in quick union, so we will skip it here. Let's talk about the union function. Here comes the important part. First, we need to find the root nodes of x and y. This is the same as quick union. And then we're going to check whether the root nodes of x and y are the same. If they're the same, they're already connected and I wouldn't have to do anything. But if x and y are not equal to each other, then we will compare the height of the two nodes. If the height of the root node of x is taller or has a higher rank, then we'll update the parent of y's root node and set it to the root node of node x. If the height of the root node of y is higher, then all we have to do is update the parent node of node x's root node to the root node of y, which is a bit tricky. So if the heights are equal, in this case it'll be the same either way, and we can choose either to be the new root node. Here, we chose the root node of x to be the root node. All we have to do is set the parent of node y's root node to the root node of node x. In this case, because they're equal, if I set the x tree to be on top, then the height of the overall tree will increase by 1. Because if the two heights are equal, we're going to choose 0 as the root node. 0 initially had height 1, and now it is 2. So if we choose 0 as our root node and also move 1 under it, now the height of the tree will become 3. So this is why we add 1 here. And finally, the function to check connectivity between x and y is still the same. We still check whether the root nodes of x and y are the same. That's all for union by rank optimization in disjoint sets. Thanks for watching.
Okay. So what is time complexity like? Of n, and yeah, find as of log n and of log n. Yeah, so we optimize this so it become of log n. What's path compression now? Path. Okay. Let's see path compression because we done this much. Okay, the answer. Okay, what is path compression? In the previous implementation of disjoint sets, notice that to find the root node, we need to traverse the parent nodes sequentially until we reach the root node. If we search the root node of the same element again, we repeat the same operation. Is there a way to optimize this process? Okay, I didn't understand this. In the previous implementation of the disjoint set, notice that to find the root node, we need to traverse the parent node sequentially until we reach the root node. Yeah, if we search the root node of the same element again, we repeat the same operation. Is there a way to optimize this process? The answer is yes. After finding the root node, we can update the parent node of all traversed elements to their root node when we search for the root node of the same element again. We only need to traverse 2 elements to find its root node, which is highly efficient. So how could we efficiently update the parent nodes of all traversed element to the root node? The answer is to use recursion. The optimization is called path compression, which optimizes the find function. Yeah, okay. So if x is equal to root x, then we return x, and for every time we don't find x equal to root x, we do root of that x and find root x. So we are continuously uh, going through the next element, and as and when we find it, we update all the all the elements back. So okay, I got this point. I probably won't go through this video because I got what they are trying to do here. So yeah, here they might have just used this guy and kept the rest of it as is. So what the time complexity would be, n is the number of vertices in the graph, alpha refers to the inverse Ackermann function. In practice we assume it's constant, in other words is regarded as O of 1 on average. Okay, summary of disjoint. The main idea of disjoint is to have all connected vertices have the same parent. So whenever I hear disjoint, then like whenever I connect, are they connected or are they not connected, so I will probably use disjoint sets. The main idea of disjoint sets is to have all connected vertices have the same parent node or root node, whether directly or indirectly connected. To check if two vertices are connected, we only need to check if they have the same root node. The two most important functions of disjoint sets data structure are to find function and the union function. The find function allocates the root node of a given vertex. The union function connects two previously unconnected vertices by giving them the same root node. There is another important function named connected, which checks the connectivity of two vertices. The union and find are essential for any question that uses disjoint data structure. Okay, cool. So let's with path union find with path. Okay, let's call it with path optimization and rank. So here we have to also this dot rank is equal to new array size dot fill 0, and what we need to do is this dot rank of I equals to 1. Initially we need to keep it to 1. So every time I come here to check for x, if x is equal to, so every time I come here to check, then I have to check if root of like the base condition would be if x equal to root of x, then we will simply return that x, because we find where the index equals value in array. We found the root or maybe call it parent node, where the index is okay, and what we do is return that x, and what we do is we keep on assigning it back to the previous elements where we did not find index the index value, like we did not find the root element. Okay, so that's that. And find, so find function is there, so let's call it, we'll be sending root, right? So root of x and root of y. Okay, if root of x is not equal to root of y, then what we'll check is, we'll check them by rank, how we can merge them. If this dot rank of root x is greater than this dot rank of root y, then what we do is this dot root of root y, we set it to this dot, sorry, root x, right? Yeah. And else if this dot rank of root x is less than this dot rank of root y, then we set this dot root of root x equals to root y. Else what we do is this dot, if they are both similar, then what we have to do is root of root any one, root y, let's say we put it to root x, and this dot rank of root x we incremented by 1, right? My system got a bit slow. Okay, so once we do this, then yeah, we have finally attached them and connected xy, find y. Okay, cool. Save. Okay, now we'll try to solve a question in the next stream, or should we solve the question in this stream itself? Okay, let's solve this. Number of provinces. So let's copy this number of, okay, otherwise let's open up the solution and we'll go directly, without looking at solution, we'll go directly to the description. Okay, super slow it is. Let me close couple of browser. Okay, so we have this. Okay, so let's read the question. There are n cities and some of them are connected while some are not. If city A is connected directly with city B and city B is connected directly with city C, then city A is connected indirectly with C. Okay, so term connected is coming in. A province is a group of directly or indirectly connected cities. Okay, and no other cities outside of the group. You are given an n into n matrix is connected, where is connected I, j, 1 the ith city and the jth city are directly connected and is connected ij0 otherwise. Okay, return the total number of provinces. Okay, so we want to perform the operation, right? So yeah, we definitely have to use quick union, but the thing is I need to also, let's open up Miro. Okay, and then what we'll do is we'll open up the Miro. Okay, let's this. Okay, go back to Miro, open this guy, select this. Okay, yeah, and okay, so we have deleted this, and okay, so let's come here and okay, so where were we? Number of provinces, right? So is connected, how many are given to us? 110. Okay, 110, 110, 001, 012, 012. Oh, um but in reality it's 123, 123. Okay, got it. Then what we'll do is, so 1 and 1, if 1 and 1 is there, we'll create 1 and 1, then 1 and 2, so there is link between 1 and 2. So 1 and 3 are not connected, 2 and 1 are connected, 2 and 2 are connected. So yeah, 0, 0 and 3 and 3. So this is our graph. Okay, so what do we need to do here? Okay, so return the total number of provinces. Got it, got it. So every time I connect anything, I need to update the numbers, right? Update the number. Okay, I see. So what we'll do is we'll create a union find. So number of nodes. So number of nodes in this one, where 1, 2, 3 are the nodes. Let's say 0, 1, 2 are the nodes and not 1, 2, 3. So it will start from 0 and we can connect everything. Whenever we see a 1, we will perform a union and find between those nodes, a union operation, and okay, got it. Okay, yeah, so let's do it. Let's do this. Let's implement this. I'll try to explain it once. Okay, let okay, so we'll perform you let's say we are just for avoiding confusion, we'll use this guy, so 0 1 and 2. Okay, so what we'll do is we'll perform union operation on whenever we see a 1, we have to traverse this entire matrix and perform union operation. So whenever we see a 1, we have to take this node, so these are vertices, right? 0 0, so we have to take this both vertices and do the operation. Okay, but we can save ourselves by doing operation. If the vertex I and j is equal to each other, then we do not do it. Then we simply do the operation on this guy, 0 0 and 1, 0 and 1, and we add them together. So this union find matrix will look like, so 0 1 2, everyone will be pointing to themselves, and when we connect both of these, so we have to also update the rank, right? Rank, so this is root array, oops, sorry, okay, root array, and this is rank array, so 0 1 2, rank is 1 1 1, and we come here, we see that the 0 and 1 needs to be connected, so we and they have rank is similar, so what we do is we change this 0 1's root to 0 and updates 0's rank to 2 because it has increased 1 2. Okay, and then what we do is here there is nothing to be done, then 1 and 0 there is a 1, but when we come here we'll check if they are connected already, so we don't need to perform the operation, so we'll be saved, and then 1 1 nothing, no need to do that, and 3 no need to do it. So we all okay, we'll be sending in number of provinces. So how will we update the number of provinces? Okay, so in the end, or every time we are performing a union operation, or we can consider all the nodes like this 3, we can consider this to be all provinces, so we can consider 3, and every time we are performing a union we can minus 1 from it, so it will become 2. Okay, yeah, so yeah, this is the value of number of provinces, right? Yeah, 2. So that's how we are going to do it. So let's code it out. For coding it out, what we need to do is we need to create our class union find. Class union find, and what we need to do is implement constructor which is connected. So first of all, what we'll be doing is if is connected dot length, if not then return 0, or else let number. So I have one doubt, like number of the rows and columns would be can be different. No, they're all same. Okay, so n will be same. It is n into n matrix. Is it? Yeah, n into n. So yeah, it's n into n. So number of provinces is equal to is connected dot length. Okay, so we'll be returning number of provinces in the end. And what we need to do is we need to loop through. We need to create let union find object is equal to new union find, and as you know, we need to send in the size of this. So number of provinces will be sent to this guy, and now we can come here and then start defining our class. So this dot array is equal to new array size, and we need to fill. Okay, and this dot root, rank is equal to new array and size dot fill 1. We can fill it with 1, and we need to for let I is equal to 0, I is less than size I plus plus. We need to fill this array, this dot array of I. So that would be every node will be pointing to itself as a root element, and then when we are finding it, so finding x, what we'll do is we'll consider x is equal to this dot array of x. If it is this case, then we'll return that x, and we'll set everything. This dot array of x equals to find this dot array of x. So we are setting everything back to the original head, and union find x and y. What we need to do is this dot array of x. Actually, we have to find x, this dot find x, this dot find y. We have to find these both, and let x is equal to let root of x equals to this, and let root of y is equal to this, and we have to check if root of x is not equal to root of y, then we perform this operation. Okay, so what we do here is that we can, we check the root. If this dot rank of root x is greater than this dot rank of root y, then this dot root of root y equals to root x. I guess we should call this root instead of rank. Right, so to avoid confusion, yeah, so this, once we are done with this, then we have to take care of another condition, else if is root of x is y is greater, then this will change, else this dot root equals to, now we have to consider y, we change it to y, sorry, root of x, and this dot rank of root of x, we update it plus 1. Okay, once we do that, then we are done. And we also need to update this dot provinces is equal to, or else we can just send is connected dot length, yeah, no need of this big word. Okay, and then size will come in, says is equal to size, yeah, and then for every connection that we make, we will be setting this dot provinces minus minus. Okay, once we do that, we also have to check connected x y, return this dot find x equals to this dot find y. Okay, once we do that, yeah, so here the main for loop starts. So let I is equal to 0. Now we'll be traversing is connected dot length I plus plus for let j equals to 0, j is less than is connected dot length j plus plus. If I equal to j, then not return, continue. If I is connected of I equal to is connected of I and j equal to 1, and this dot, do we need to do this? Okay, so what we'll do is we'll directly union find object dot union of I and j and return union find obj dot provinces, right? Yeah, so once we do that, I guess we should be able to get the results if I haven't made any mistake. Okay, I have. Oh, I have called it just called it union. If I now run this, it cannot read property of undefined, dictating 0. How is that possible? Size. Okay. Test cases. How is this possible? Like we are passing in this. Oh, this dot find. Now I run it. It should cannot read. Why? Okay, I'll be right back in a couple of minutes. Okay, let's start where we left off from. So union, this dot find, this dot find y. Okay, so where I might be going wrong, let's see. Cannot reading 0. Cannot read property of undefined. How can it be undefined? So when we do this, let's console log the root is dollar this dot root. Okay, we can't even get there. Okay, so new union find object is connected. So let's not do this, and let's okay, sorry, okay, let's not call this guy. Okay, just run this and show me what is connected. No, show me. I'm creating this union find console dot log. Okay, undefined is coming in, but I did do this right. Console log root is union find obj dot root. Okay, then this, then run this bad boy. Okay, undefined. So am I not defining class properly? Union find. Oh, root is undefined. How come? How come it is undefined? Okay, let's see submissions. Okay, so I've done the same thing. Class, I've defined a class. So okay, let's pick this bad boy from here. I've done the same thing, but looks like there's a bug. something of that sort. And if I run this now, yeah, I know. If I run this now, okay, now it's coming. Okay, so let's just do this and provinces. Okay, cool. I don't know what the error was there. What was the error? But yeah, we are able to do it. And here we go, boys.